A machine the size of a small house is orbiting a point in space where gravity nearly disappears, and with every hour it spends there, our sense of scale is quietly unraveling. The James Webb Space Telescope was not built to make the universe prettier. It was built to answer a single uncomfortable question. How big, how old, and how strange is reality really? What it has begun to reveal is not reassuring. It suggests the universe is vastly more crowded, more extreme, and more incomprehensibly large than we ever allowed ourselves to imagine. Webb sits nearly 1 million miles from Earth, far beyond the reach of repair, locked into a delicate gravitational balance where it can stare into deep space without interruption. From that distance, it does something no human instrument has ever done before. It listens for heat so faint it borders on nothingness. Light that has been traveling for more than 13 billion years, stretched thin by an expanding universe, arrives not as visible glow but as cold infrared whispers. Webb was designed for this task from the ground up. Its segmented mirror, wider than a tennis court, is coated in gold not for spectacle, but because gold reflects infrared light with extraordinary efficiency. Its massive sun shield blocks almost all heat from the sun, Earth, and Moon, allowing the telescope to cool to temperatures colder than Pluto's surface. Only at such extremes can ancient light be separated from the telescope's own warmth. This engineering is not excess, it is necessity. Because the universe hides its earliest secrets in wavelengths no other observatory could see. As space expands, it stretches light itself. What once blazed as ultraviolet radiation from the first stars is now elongated into infrared by billions of years of cosmic growth. Webb is not simply looking far away, it is looking back, into epochs so early that the laws we rely on begin to feel unstable. Every distance in the universe is also a measure of time. When Webb detects light from a galaxy 10 billion light-years away, it is seeing that galaxy as it existed 10 billion years ago. There is no way around this. The sky is not a snapshot of the present. It's actually a layered archive of the past. Nearby stars appear almost as they are now. Distant galaxies appear as ghosts from a younger universe. And, the most distant objects are seen as they were shortly after everything began. For decades, astronomers believed they had a rough outline of how the early universe should look. After the Big Bang, matter cooled. Gravity slowly gathered gas into the first stars, then into small galaxies, and only much later into large, complex structures. Light was expected to emerge gradually. Order was supposed to take time. Webb has, shattered that expectation. When the telescope began its deepest surveys, pointing at regions of sky once considered nearly empty, the darkness collapsed. What appeared instead were thousands upon thousands of galaxies packed into tiny slices of space. Not faint smudges barely forming, but bright, structured systems already producing stars at astonishing rates. Some of these galaxies existed when the universe was less than 500 million years old. According to previous models, they should have been rare, small, and dim. Instead, Webb found many that rival the brightness of mature galaxies like our own Milky Way. The implications are, unsettling. Brightness means mass. Mass means stars. Stars mean time. For a galaxy to shine so strongly, it must have formed stars rapidly and efficiently, converting vast clouds of gas into light in far less time than theories allow. In some cases, the inferred stellar mass is so large that it challenges whether the universe had enough time to assemble it at all. Scientists did not accept this lightly. They questioned the distances, suspecting that some galaxies might be closer than they appeared. They accounted for gravitational lensing, where massive foreground objects magnified distant light. They tested whether dust could be altering the signals. They ran independent analyses with different assumptions. Again and again, the conclusion remained the same. These galaxies are real, they are distant, and they are far too developed for their age. As Webb's instruments dissected their light, the shock deepened. The spectra revealed heavy elements such as carbon and oxygen embedded in these early systems. These elements do not emerge from the Big Bang. They are forged in the cores of stars and scattered through supernova explosions. Their presence means that entire generations of stars lived and died before the light we are now observing was even emitted. In cosmic terms, that is astonishingly fast. Then came the black holes. Webb detected signatures of actively feeding supermassive black holes in galaxies that should barely have existed. Some already weighed millions of times more than the Sun. Growing black holes at that scale is slow work, limited by how much matter they can consume without blowing it away. Yet here they were, fully formed, less than 500 million years after the universe began. The math, honestly, strains to accommodate them. These discoveries suggest that the early universe was not a quiet place slowly organizing itself. It was violent, efficient, and wildly productive. Stars formed rapidly. Galaxies collided and merged early. Black holes may have grown from massive seeds we do not yet understand. The universe did not ease into existence. It erupted. As Webb's surveys expanded, so did the scale of what we could count. In one of its largest mapping efforts, astronomers catalogued hundreds of thousands of galaxies in a patch of sky barely larger than the full moon. When those numbers are extrapolated across the entire sky, the total count of galaxies in the observable universe balloons into the trillions. This is not speculation. It is a conservative estimate based on direct observation. Trillions of galaxies, each containing billions or, even hundreds of billions of stars. These are numbers so large they really resist our intuition. But even this vast inventory, it only represents what lies within our observable boundary. The universe itself, well, it extends far beyond what any telescope can see. The observable universe has a radius of about 46 billion light-years. Now, this number confuses many people, because the universe is only 13.8 billion years old. The explanation, though, lies in expansion. Space itself has been stretching since the beginning, carrying galaxies away from one another. Light traveling toward us has had to cross an ever-growing distance. The result is a cosmic horizon that's far larger than what simple age-time speed would suggest. Beyond this horizon lies the unobservable universe. These are regions so distant that, honestly, their light will never reach us, no matter how long we wait or how advanced our technology becomes. Those galaxies are receding faster than light itself because of the expansion of space. They're not just far away, they're causally disconnected from us forever. And even the observable universe is, well, slowly slipping away. Dark energy, this mysterious force that permeates space, is actually accelerating expansion. Over immense timescales, distant galaxies will fade beyond the horizon one by one. Future astronomers, if any exist, may see only a small, isolated cluster of nearby galaxies surrounded by darkness, completely unaware that a vast cosmos once lay beyond. What makes this even more humbling is how little of the universe we can actually see or touch. All the stars, planets, gas, and dust account for less than 5% of the universe's total content. The rest is invisible. Dark matter outweighs visible matter by more than 5 to 1, shaping galaxies through gravity while refusing to emit or absorb light. Dark energy dominates everything, pushing space apart and dictating the ultimate fate of the cosmos. Webb has also stepped into one of the most troubling puzzles in modern physics, the expansion rate of the universe. Measurements based on the early universe suggest one value. Measurements based on nearby galaxies suggest another. Webb's precise observations support the higher, local value, deepening a disagreement that has no easy resolution. If both measurements are correct, then something fundamental about our understanding of physics is missing. This is where the true terror of Webb's revelations lies, not in monsters or catastrophe, but in scale and ignorance. The universe is not just bigger than we thought. It evolved faster, structured itself earlier, and hides most of its substance in forms we barely understand. Vast regions of reality are permanently inaccessible, not because we lack imagination, but because the universe itself forbids access. The James Webb Space Telescope was meant to refine our cosmic story. Instead, it has exposed how incomplete that story is. With every deep image, the universe appears less orderly and less predictable than our models suggest. The more clearly we see, the more we realize how much remains unseen. We are not standing at the edge of understanding. We are standing inside something so immense that even its observable fraction overwhelms comprehension. Webb has not shown us the end of the universe. It has shown us how small our corner truly is, and how vast the unknown will always remain.